Okay, so here we go. Are you going to cooperate, little thing? There we go. Alright. So, we have that container of water. You have all your dimensions, so I'm going to say, well, the pressure of the atmosphere plus rho g h plus y, because I'm starting at the top, plus 1/2 rho b at the top squared, which is 0. We're assuming it starts from rest, is equal to the pressure of the atmosphere, plus rho g h. And this is at the bottom, so it only has to follow that h. And 1/2 rho bf squared. Alright, is everybody okay with that? So these will be the same. So I have rho, which is the same for everybody. So I have G is 9.8. H plus Y is 0.35 plus 0.75, which is 1.10, is equal to rho, which got canceled out, gravity, height of 0.75 meters, plus 1/2 bf squared. Okay, so when I do that math, I got the speed that it hits the ground to be 2.65 meters per second. Alright, and they want to know dx. Well, dx is equal to vxt. Well, we have our vx, that's no big deal. We need our t. So I need to find how long it takes it to fall. So I said t is equal to the square root of 2 dy over g. So it's going to fall 2 times 0.75 meters over 9.8. So t is going to be 0.91, I think I got. Yeah, no, 0.391. 0.391 seconds. So 2.65 times 0.391 gives me a dx of 1.04. Alright, then it says, what effect would increasing the diameter of the hole in the container from 0.25 to 0.5 centimeters have on the answers to A and B above? Okay. So let's talk about that. So the speed of the water remains the same. We just have more water comes out. More water comes out. Because remember, flow rate Q is equal to A, B. Well, this is going to increase. So let me make sure that's going to increase, so that's going to increase, but this has got to stay the same. Alright, then it says, part B, the distance where it lands. Well, if V doesn't change, dx can't change. Because remember, dx is vxt. Well, vx didn't change, and the height of that it fell from didn't change. So it has no impact on it. Okay? Alright. So let's go on. Okay, there's our next one. So we have this little raft. And it is a ship carrying cargo into a port is hit by a sudden storm that causes one of the cargo containers to fall overboard, sink to the bottom of the ocean. Ocean depth is 18 meters. Container itself is 2,400 kilogram mass. Cargo is 9,000 kilogram mass. And they want to tell you the density of the ocean water, and they want to know the gauge pressure. Well, pressure from the gauge, or gauge pressure, ignores atmospheric pressure, so it's just rho GH. Rho is 1025. Gravity is 9.8. And the height is 17 meters. So I got the gauge pressure to be 1.7 times 10 to the 5th pascals. And then B says, calculate the total downward force exerted on the top of the container. So we have the atmospheric pressure, which is 100,000 pascals, plus the gauge pressure, which was 1.7 times 10 to the 5th pascals. So that's the pressure. And we're looking for the force. Well, force is pressure times area, and the area is 2 by 4. So the force is going to be 2.2 times 10 to the 6th newtons. Alright, oops, that's not too good. Okay, then it says a rescue ship with a crane is sent to retrieve the cargo using a cable attached to the top of the container. The ship hoists the container at a slow, constant rate, so all the forces are balanced, assuming no resistance due to the water. Determine the tension in the cable. Alright, well, let's look at that. So here's my package, my crate. So I'm pulling up like that with tension. The buoyant force is pushing up like that, and gravity is pulling down. And since the velocity is constant, I know that buoyant force plus T has to equal mg. So T is going to be mg minus buoyant force. Oh, buoyant force right there. So mg is the 3,300 kilograms for everything, the container and its contents, times 9.8. The buoyant force, I said, was rho GB minus rho GV. Rho was 1025. Let's get rid of that right there. (1025) kilograms per cubic meter. G is still 9.8. And the volume of the container is 2 by 4 by 1, so that's 8 cubic meters. So when I did that, I got my tension to be 31,000 newtons. Oops, so that wasn't any big deal. Oh, now my pen's acting all crazy because it's running out of juice. Alright, and let me pause. Okay, then it says on the graph below, sketch the tension in the cable as the container is lifted out of the water at a steady rate. So tension is going to remain constant here. I don't know if this is going to work. Come on, we're almost through. Okay, so we got to draw the tension in the cable. So it's going to be, should be constant right there. It's not a very straight line, but that's constant at 31,000 newtons. And then once we get it out of the water, we know that this tension is going to be equal to the weight. So I think that's 110,000 newtons, yes. And that came from 3,300 kilograms times 9.8. So as we were going from the top of the container, busting the water, and lifting it all the way up, the tension is going to increase linearly, and that's what your graph looks like. Alright, and then I think we have a little bit more. There we go. So let's finish out this problem before my pen quits working. Alright, well. Okay. It says all of the cargo is removed and the container is placed back into the ocean where it now floats. Calculate D, the portion of the container below the water line. So how much of the container is in the water? So I said that the force of gravity was equal to the buoyant force. So I said mg is equal to rho GV. And the G's will cancel. So the M is going to be equal to rho times the volume, which is length times width times the D that we're looking for, the height. So the mass of the container is only 2,400 kilograms. 2,400 kilograms. Rho is 1025 kilograms per meter cubed. And length times width, that's 8 meters squared times whatever D is. So I solve for D, and I got D to be 0.29 meters. So I'm hoping I'm done and I can put these on YouTube. Let me see. Yes, we're on multiple choice now. Okay, good luck.